So welcome everybody to the second day of this annual meeting. So my name is Christian Selmek. I'm part of the organizing committee and I have the great pleasure to chair the first talk today. And I'm happy to introduce our speaker, Daniel Huybrechts from the University of Bonn. So Daniel is a complex algebraic geometer, and I think it's fair to say he's one of the most renowned experts in the theory of hyperkähler manifolds, very important class of complex manifolds. And as you all can see, he's going to tell us more about this today. So Daniel is in Bonn since 2005. Before he had positions in Paris 7 and in Cologne. And even before he was a postdoc in Essen and at the École Normale in Paris. And well, he is the worldwide recognition. He has been a speaker at the ICM in 2010, has supervised 14 PhD students, and some of them already hold positions themselves. Recently he's been awarded, together with Claire Voisin, Olivier Debat, and Emanuele Macri, a so-called ERC Synergy Grant, probably one of the biggest grants one can get in Europe for fundamental research. And I want to point out particularly that Daniel has written several wonderful books, which are all of them classics in the field, like on modular spaces of sheaves. This is a book, Generations of Algebraic Geometers Learned Modular Theory from it, on Fourier-Mukai transforms, and recently writing a book on cubic hypersurfaces. And I think you can still download the draft from his homepage, and looks really, really nice. So we are very happy that Daniel accepted our invitation. And so we are looking forward to his talk on geometry of K3 surfaces and hyperkähler manifolds. And I should just point out that in all plenary talks, you can ask questions using the Q&A tool. There's a button down in the Zoom application, and I will read these questions at the end to our speaker. Daniel, the stage is yours.
Thank you very much for the kind introduction, Christian. So I hope you can all see the slides and hear me well. So the title of the talk is Geometry of K3 Surfaces and Hyperkähler Manifolds, Open Problems and New Perspectives. Before I dive into the talk, however, I'd like to make sure to give you this link to my webpage. In my talk, I mentioned many results due to various people, and I have omitted all the references on the slides. And I give precise attributions and complete references in this PDF, which is essentially the write-up of the talk. Okay, so I also wish to thank the organizing committee for giving me the chance to make some publicity for research direction in algebraic geometry, which I find fascinating, which has a long history with roots going back decades, which always at the same time has seen a constant innovation. The geometry of K3 surfaces and hyperkähler manifolds has played the role of a testing ground for new ideas, new techniques. Very much like the theory of abelian varieties, general methods, new techniques, big conjectures have first been tested for K3 surfaces before, and then fine-tuned there before then applied to more general situations. Maybe the best example, well, probably the best example is Stellinius' proof of the Weil conjectures for K3 surfaces in the early 70s. Before he then went on to prove the Weil conjectures a couple of years later in full generality. The paper is a wonderful example because not only does he prove the Weil conjectures for K3 surfaces, but actually develops tools that are still used today. It's, I think, maybe the first paper where Grothendieck's philosophy of motives is really applied to concrete geometric problems. There are other more recent examples of this. For instance, the Tate conjecture in DB2, the analog of the Hodge conjecture, has a couple of years ago proved 4 K3 surfaces. It's still open in general, even in DB2. But even proving this, those conjectures for K3 surfaces lends a lot of evidence, credibility to the conjectures in general. Okay, so now I thought about how to motivate, why should you be interested in K3 surfaces and hyperkähler manifolds, and I decided to start with the theory of Riemann surfaces, compact orientable surfaces. For an algebraic geometer, which is a little confusing, those are called algebraic curves. So you always have to pay attention what I mean, real dimension or complex dimension. So as you know, the compact surfaces are classified by their genus. So genus 0, that's just the sphere, and genus 1, these are tori, as you can see here. And then the compact surfaces of higher genus. So the genus is just the number of holes. So this would be genus 2 here, and that's all you can have. Every genus is of course possible. Once you fix the topology, so that means you fix the one numerical invariant we have, the genus. You want to enhance this in order to do geometry. And there are various ways of doing this. One would be by introducing a conformal structure or Riemann metric, or you could maybe introduce a complex structure. That means you cover, for instance, this torus here by small open subsets of the complex plane C, and you want the Gluing maps between these open subsets to be biholomorphic, and then that means you can talk about holomorphic functions on this Riemann surface. Or you describe the surface like this in terms of algebraic equations. In dimension 2, so real dimension 2, all these three options actually in the end lead to the same kind of geometry, which is not true in higher dimensions anymore. So if we do this for genus 1, so we fix the genus now to be 1, then as a complex geometer, you would maybe think of the elliptic curve as just a torus, so C divided by some lattice gamma, where the lattices of the form Z plus Z2. So tau here would be an element in the upper half plane. So its imaginary part would be positive, and you can actually see that this defines this quotient is really a torus, because if this is tau, then you identify the opposite edges of a parallelogram, and that gives you then topologically really the torus we've seen before. Or if you are more algebraically inclined, you could describe a surface of genus 1 or an elliptic curve as a zero set of a cubic equation. So for instance, the cubic equation y squared equals x squared x cubed plus ax plus b. To have an explicit example in mind, you could look at the Fermat equation, x cubed plus y cubed equals 1. So this is here the Fermat equation, and we look at the zero sets in the complex numbers, and we have to compactify it by adding a point at infinity to make this really a compact surface. If you are interested more in the arithmetic of these cubic equations, then you would take an equation like this and just look at solutions not in the complex numbers but in the integers or in the rational numbers or in some finite field FB. Okay, so I'll be mostly interested in the geometry in this talk and not so much in the arithmetic. So we have then these two options describing an elliptic curve as a quotient C by some lattice gamma, or as the zero set of a cubic equation, for instance, this Fermat equation here. So if we now venture into higher dimensions, let's say dimension 2, so now this means complex dimension 2, real dimension 4, we have these two options, starting with these two descriptions of elliptic curves. And so we could, for instance, just write down a torus, now the complex two-dimensional vector space by some lattice, so now the lattice will be of rank 4, so Z to the 4. That's the wonderful topological complex manifold. Writing it as a quotient like this, you know what it means to have holomorphic functions, which functions are holomorphic on this quotient, because locally it really looks like open subsets in C2. Unlike the one-dimensional case, complex one-dimensional case, most of these quotients cannot be described by algebraic equations. And even if they can, it's usually very hard to write down the equation if you're just given this as a quotient with an explicit lattice gamma. If you like the other description of elliptic curves as a zero set of a cubic equation better, then why not looking at the Fermat equation of this form now in one more variable, so x to the 4th plus y to the 4th plus z to the fourth equals 1. I raised the degree from 3 to 4 in order to keep some curvature properties, which is important later on. The difference here to the one-dimensional case is that those sets of solutions cannot be uniformized anymore. So there is no natural way to describe them, for instance, as a quotient of C2 divided by gamma. So there's no uniformization anymore for solution sets of these equations. So in this talk, I'll stick to this generalization. So Fermat equations and solution sets of these equations in the complex numbers have been dubbed K3 surfaces. The name was invented by André Weil to honor 3 mathematicians, Kähler, Kodaira, and Kummer, and as he later explained, also et la belle montagne K2 au Kashmir. There is in fact also a K3 mountain peak, and André Weil should have known, and this, what you see here on the right, is actually a picture of the K3 mountain peak, which is the 12th highest mountain in the world. But it is certainly smaller than the K2. So I would like you to think of K3 surfaces and the higher dimensional versions of those hyperkähler manifolds as the more interesting alternative to replacing an elliptic curve, so C divided by gamma, just by a complex torus of higher dimensions. Okay, so this is like the message of this talk. Instead of doing this generalization, which is interesting, you could look at another generalization which is as natural as complex tori, and you find a different sort of geometry and a lot of interesting phenomena to explore. So what is the official definition now of a K3 surface? Here it is. It's a simply connected manifold, a complex surface. So that means you glue small open subsets in C2 by biholomorphic maps to a global structure, and you assume it to be compact, and you also assume it, to simplify the topology, to be simply connected. So that means every closed loop on this form manifold, so it's a real form manifold now, can actually be contracted continuously to a point. So that's the compact surface, complex surface, and you want it to come with a holomorphic symplectic structure sigma. So locally, this looks like dz1 wedge dz2. So z1 and z2 are holomorphic coordinates on these open subsets of C2 by which you covered your surface. This you cannot glue to a global 2 form, but you require that you can glue it if you change it by a scalar function, and you want this function, of course, to be holomorphic and to have no zeros whatsoever. So that's a strong condition. That's a strong condition you impose. For instance, in this example of the Fermat quartic here, you could write down a holomorphic proof and explicitly as a residue of a 3 form. So you could write a dx, which dy, which dz. So that's a 3 form on the ambient 3-dimensional space. And if you take the residue of this thing with a pole, and you get a pole along the 0 set, if you divide by the equation of the 0 set, then you actually find a 2 form on this complex surface. Okay, the same definition works in higher dimensions, more or less. So a hyperkähler manifold is a compact complex manifold. Now, Daniel, yeah?
You haven't written the equation in the denominator, have you?
Oh, you don't see the residue? No,
but I mean, isn't it the degree 4 equation?
I'm sorry. Yes. Oh, yes. Too much cubics. Yeah. Thank you, Klaus. That's 4. Thank you very much. Yeah, that should be the quartic equation. So hyperkähler manifolds, you use the same definition. You want it to be a complex manifold. So now you glue small open subsets in some high dimensional complex space via biholomorphic maps. You want the whole global structure to be compact. You want it to be simply connected to simplify the topology, and you want it to have a whole symplectic structure. So now you have more local coordinates. For instance, you could write down symplectic form like this. Again, these local forms, they will not glue, but if you multiply them with holomorphic functions, certain linear combinations of those are supposed to glue to a global symplectic holomorphic form. To simplify the theory, you assume that this is essentially unique up to scaling it. And then there's a technical condition. You want this to be a Kähler manifold, which is automatic once you can describe the complex manifold in terms of polynomials. So this is the definition of a hyperkähler manifold and before of a K3 surface. And I hope somehow by now you're interested in these and you would like to know what does it actually mean to study the geometry of these objects, which are generalizations of elliptic curves, and I claim more interesting than complex tori. So the first question we always ask is, if I fix the topology, so we did this for Riemann surfaces, in how many ways can I actually do geometry on them? So you want to enhance it by either putting a conformal structure on it, and then here, you know, on the sphere, there's only one conformal structure, and that gives rise to the complex projective plane. On the elliptic curve on the torus, you have actually a one-dimensional family of putting complex structures on here. So this is essentially given by the parameter tau. So remember, we wrote down an elliptic curve as the quotient of C by some gamma, where the gamma was determined by a parameter tau. So the tau was an element in the upper half plane. And this is the complex parameter you have. That parameter has all the possibilities of putting a complex structure or conformal structure on this Riemann surface. If you go up with the genus, the higher the genus get, the more options you have to put a complex structure on a topological surface. They all together make up a 3G minus 3-dimensional family, and this is what algebraic geometers call the moduli space MG. This is a very classical object. This goes back to Riemann. Now we can do the same thing for, can try to do the same thing for K3 surfaces. So let's look at now the Fermat quartic equation. Make sure it is the quartic. So the set of solutions, complex solutions, it has a certain topology, and now you can ask, you know, how many ways can you actually put a complex structure? Can you do geometry on this thing? And it turns out that there is a high-dimensional space. It's actually a 20-dimensional space, which unfortunately is rather wild. So it's not a nice space. It's wild and ergodic, and only if you restrict to those complex structures. So again, a complex structure is the way you can cover your topological manifold by open this in CN and glue via biolomorphic maps. Only if you restrict to those that can be described as zero sets of polynomial equations, then you get nice moduli spaces, 19-dimensional moduli spaces. They depend on, let's say, the degree, what we call the degree, which is roughly the degree of the polynomials you need to describe the K3 surface. So these moduli spaces MD, they turn out to be as interesting as intricate as the moduli spaces MG. And people who have studied traditionally the global structure of the moduli space MG have turned to studying the global geometry of these moduli space MD of all complex structure on the topological manifold underlying just this Fermat quartic surface. Okay. There's, however, one thing I haven't explained yet, namely so what we did before was, for Riemann surfaces, we fixed the topology and then looked at all the possible complex structures. You can do, of course, the same thing in higher dimensions. Somehow the situation is very easy, or if you prefer, it's a little boring. Topologically, elliptic curves and abelian varieties are always the same. It's always a torus, Cn divided by gamma. That's by definition. And topologically, nothing interesting happens. It's really just the product of a circle. So it's a high-dimensional torus. So the situation is much more interesting for K3 surfaces and hyperkähler manifolds. First of all, it's not obvious at all what the topology is. It's harder to draw. So what you see here on the right is a real cut of the Fermat equation, slightly singular, but nevertheless. Since the K3 surface is of real dimension 4, I cannot give you a picture of the actual thing. So this is the best you can have. And it turns out, again, for K3 surfaces, there's only one topological structure. So all the K3 surfaces, although I gave you a general definition of a K3 surface, which in principle would allow for several topologies, there's only one. So again, as for an elliptic curve, all elliptic curves, they take place on one torus. For K3 surface, the same. All K3 surfaces actually take place on the topological manifold underlying the Fermat quartic. The situation becomes slightly more interesting if you go up in dimension now for hyperkähler manifolds. Unlike the case of K3 surfaces and elliptic curves and the Abelian varieties, we have more possibilities for the topology. At the moment, we have two different distinct topological types in each dimension. And in addition, in dimension 6, we have one more, and also in dimension 10. This is certainly one of the urgent questions in the theory. Can we actually describe all the possible topologies? The community is a little divided. Some people think essentially we have seen them all. Maybe there's one more or two more. Other things, there may be plenty of them. We don't have any general results in this direction. There are only very few topological restrictions, but maybe this is somehow depends on the distance from which you look at the problem. But there are actually heavy topological restrictions on the topology of a hyperkähler manifolds. That makes us hope that we can actually classify them. But the question as such is largely open. Okay, now suppose we have fixed one of the topologies. So for K3 surface, there's no choice. And even for high-dimensional hyperkähler manifolds, we probably don't have many choices, but there's some choice. Suppose we also have fixed a complex structure. So we have covered the manifold by open disk and CN. Now, what are the kind of questions we would like to ask for these complex manifolds? So I put down some typical structures, some typical questions. The first one could be, I mentioned that if even the Fermat quartic, so a very explicit equation, we have no way of uniformizing the K3 surface. So it's certainly not a quotient C2 by some letters. But you could ask the question, maybe is there a map, a holomorphic map from C2? So that's C2. So here's my surface or hyperkähler manifold. Is there maybe a map, holomorphic map from C2 to any K3 surface with a two-dimensional image? So I put this down as a condition that the determinant of the Jacobian is not constant 0. That's an open question that we don't know. You could ask a similar question. In fact, these two are more or less equivalent. You could ask first an easy question, which we do know to answer. Can we prove that there's a holomorphic map from C, what we call an entire curve from C to any surface? Of course, you want this to be non-constant, otherwise it's not so interesting. This question we can answer, but what we don't know is, and this is essentially equivalent to the first question, is whether there exists an entire curve that's also dense in the surface. More algebraically, we could ask for rational curves. So are there a rational curve is just a holomorphic map from the complex line? Remember, this was just a Riemann sphere, and we fixed the conformal structure on it. And so we're asking for holomorphic maps from P1 to S. So is there always a rational curve on any K3 surface? We do know the answer to this. This is recent work of many people. The last one is by Liedtke, Chen, and Cornelas, proving that every algebraic K3 surface has, in fact, infinitely many rational curves. The question becomes more interesting if you ask for criteria that tell you when can you find a rational curve through a given point. So you fix not only the K3 surface, but actually a point on it. And now you would like to know, is there a rational curve through this point? You can turn this into a question with a more arithmetic flavor, but there's no criterion that would tell you exactly when this is the case. You can make this question more interesting, for instance, by asking not only just fixing 1 point, but 2 points. Or you could ask, is there always an elliptic curve through every point? Also, we know the answer to the last one. So there is, in fact, an elliptic curve through every point. But you could ask, is there maybe an elliptic curve through every given 2 points in the surface? A third type of geometries would concern bundles, so holomorphic bundles. So if this is your surface S, we know what topological bundles are, so the fibers of those will be Cn. And if you want the gluings for the bundles also to be holomorphic, this gives you the notion of algebraic or holomorphic bundles. And following questions work by going back to André, Grothendieck, and Narasimhan Seshadri, you would like to parentize all these bundles and see what the global structure of this modular space is. Or you could even ask for the existence of bundles. So, for instance, for given Chern classes, so given topological structure or Chern classes in some other cohomology theory, you would like to know, are there bundles realizing these Chern classes? And this is largely open in higher dimensions. Okay, so this is the kind of questions, of naive questions you always would like to answer. And no matter what you want to do, you need a technique, a tool to approach these things. The only tool, essentially the only tool we have is linear algebra, it's Hodge theory. So I'll spend some time explaining the abstract notion of Hodge structures. So I'll restrict myself to Hodge structures of weight 1 and weight 2, and then explain how they come up in the theory of K3 surfaces. So so this everything I explain on this slide, you can actually teach in a linear algebra class first year. Usually we don't, but in principle you could. So what we need is we have to start with a lattice, so a lambda that's isomorphic to Zn or to Qn, which then gives you the complexification of it, which is isomorphic to just the complex vector space Cn. And then a Hodge structure of weight 1 is nothing but the decomposition of your vector space, complex vector space, into 2 subvector spaces, which we call lambda 1, 0 and lambda 0, 1. So these are complex vector spaces. And there's one additional condition, that's that these 2 vector spaces are complex conjugate to each other. So if you have a vector that happens to be contained in lambda 1, 0, then its complex conjugate has to be in lambda 0, 1 and vice versa. So the power of this notion is really the interplay between the integral structure or the rational structure and this decomposition as a complex vector space. Note that you have to start with one of these structures, otherwise you wouldn't know how to explain, how to say what the complex conjugate is. Only if you fix the isomorphism with Cn like this, which you get by from an isomorphism like this, you know how to conjugate a vector in an abstract complex vector space. If you just give yourself a abstract complex vector space, you don't know how to complex conjugate. So here in this, what you see in this picture here is the vertices of this grid are the elements of the lattice, and the red line is the red line here is the complex vector space, let's say lambda 1, 0. Okay, and so the power comes from the interplay between the 2. For instance, here you see that this line contains an integral point, so that element of the lattice. But you see the other points here, these are in the picture, I think these are the only points that are contained at the same time in the lattice, in the lambda, and in the complex vector space. You also see that the notion is not rigid. Once you have a decomposition like this, you can start moving your line here, your lambda 1, 0, and you get define the lambda 1, 0, 1 as its complex conjugate, and you get a whole family of these complex decompositions. For some lines will contain vertices of the grid, so lattice points. Some others won't, and you get an interesting family of this non-isomorphic structures. A Hodge structure of weight 2 is something similar. Now you look at a decomposition in 3 parts. So you have a lambda 0, 2, lambda 1, 1, and lambda 0, 2, 2, 0, 1, 1, and 0, 2. These are again complex vector spaces. you want the 2, 0 to be complex conjugate to the 0, 2, and the 1, 1 to be complex conjugate to itself. And again, the power of the notion comes from the interplay between this complex vector space decomposition and the lattice. For instance, you could look at the intersection of the lattice with the 1, 1 part, and that's a lattice, a sublattice of the original lambda. It might be completely zero, but sometimes it's not. And an important invariant of the structure is the rank of this sublattice. So there's a completely abstract way of passing from weight 1 Hot structures to weight 2 Hot structures by just taking the exterior power of of lambda, and then you define the for instance the new 0 or 2, 0 part as the wedge 2 of the old 1, 0 part, or you define the 1, 1 part as the tensor product of the 1, 0 plus tensor the 0, 1 part. There's also a kind of converse to this construction. You might think of this as the kind of left adjoint to this construction, which is what we call the Kubercete construction, which works in case the 2, 0 part is one-dimensional, and it then associates to a weight 2 Hot structure on the right, a weight 1 Hot structure on the left. This allows you to pass from one to the other, but it needs this additional condition that the dimension of the 2, 0 part is actually 1. Okay, so now how do these abstract linear notions come up in geometry? Let me start with weight 1 and maybe look at the 2-dimensional torus as we did before. Then we do get the lattice lambda as the first cohomology with values in the complex numbers. If you don't know about cohomology, it's not really important. We just take the original lattice gamma or its dual. So that's by definition. So in this case, this was isomorphic to Z4, the lattice gamma, and you get your lattice lambda. And then a Hodge decomposition of this first cohomology of this lattice gamma would be a composition in 1, 0 part and 0, 1 part, where now the 1, 0 part is generated by two differentials, two natural 1 forms, dz1 and dz2. And the 0, 1 form part is then the complex conjugate of this one. So note that Z1 and Z2, they are functions on C2, but they're certainly not functions on this quotient anymore, but their differentials dz1, dz2 are in fact global 1 forms on the quotient. A similar structure exists for Riemann surfaces. So now think of a Riemann surface with a fixed conformal structure or complex structure, and then you take the lattice lambda, which really is generated by the obvious loops you see here in this picture. And it does come within intersection form, so you know how to intersect like the red loop here with the blue one. That would give you intersection number 1. The two blue ones, this one with this one does not intersect. That gives you intersection number 0. So this is this thing here is an alternating symplectic form with integral values on this lattice here, which is of rank Z to G. And then the Hodge decomposition in this case is the decomposition in a 1, 0 part and a 0, 1 part. So again, Hodge structure of weight 1. It's G-dimensional, so locally you have holomorphic coordinates, and locally you can look at holomorphic forms of this type. The dz itself will not globalize, unlike the situation for complex torus we had before. But you have some choice here for the f, and in the end you find the G-dimensional space of global 1 forms on a Riemann surface. So the typical examples of the goal in Hodge theory, the type of results we aim for is the Torelli theorem. I state two versions of it for tori and for curves or Riemann surfaces. The one is rather trivial, and the second one is certainly not. It's a classical result, but its proof is certainly far from from trivial. So the first one says the following. So I take two tori T1, T2. So just think of tori, you can stay in dimension 2, C2 by some lattice gamma I. So the complex structure really is given by how the lattice gamma I sits in the C2. It's almost immediate that these two tori are isomorphic, really, so they exist the bijection between the two, which is a holomorphic map in both directions. If and only if there is an isomorphism of these lattices H1 of the two tori, so these are just lattices gamma I. So maybe let me write here gamma I, gamma 1 star, and gamma 2 star, and you want this to be compatible with the Hodge decomposition in the 1,0 part and 0,1 part. Okay, so this is this compatibility here. So that's the Torelli theorem for tori, which is, as I said, rather elementary. But for curves or Riemann surfaces, it says the same, and it's much harder. So two Riemann surfaces are the same Riemann surfaces, so there exists the bijection that is biholomorphic or compatible with the conformal structure in both directions. If and only if there exists an isomorphism of these lattices that is compatible with the Hodge decomposition. Now it's the Hodge decomposition for the Riemann surface. And this pairing, I briefly explained so this natural symplectic structure on this lattice, which I introduced here by saying I intersect red loops and blue loops and get an intersection form on this lattice. So despite its despite this being a very classical result, there are certain aspects of this result we still don't really understand. For instance, you could naively ask, what happens if I just drop this condition, to be compatible with a quadratic form? Okay, so now you just look at Riemann surfaces that have the property that their first cohomologies are the same, Hodge structures. What does it mean for the curves or the Riemann surfaces? You can rephrase this in terms of geometry by saying that their Jacobians are the same. I'm not going into this, but as unpolarized abelian varieties. But we don't really know how often this happens. So this is a phenomenon that hasn't really been studied, and somehow one feels there is still aspects that we haven't really understood. So now if we go to dimension 2, there are geometric objects to which you naturally associate a Hodge structure of weight 2. Let me begin again with the case of tori. So again, I start with the torus of dimension, let's say 2. But now I'm not looking at the first cohomology as we did before, but at its second cohomology, H2. Again, if you don't know what cohomology, just think of this as the wedge 2, so the second exterior power of this first lattice. And then the Hodge structure of weight 2 on this lattice now is a decomposition in the 2,0 part, the 1,1 part, and the 0,2 part. And it really is this general linear algebra construction applied to this weight 1 Hodge structure, taking just wedge 2. So the 2,0 part is really just the wedge 2 of the 1,0 part we have seen before. So it's spanned by dz1 wedge dz2. Something similar happens for K3 surfaces, and then for hyperkähler manifolds, you look at the lattice lambda, which is now the second cohomology. So you now just think topologically of this thing spanned by all the compact surfaces that sit in your 4-dimensional manifold, and it comes with a natural pairing, measuring the intersection of two surfaces and how many points they intersect. And it comes with a natural decomposition, a weight 2 structure, so that means you have 3 vector spaces, the 2,0 part, the 1,1 part, and the 0,2 part. There is some additional compatibility with the intersection form. You want this to be roughly orthogonal with respect to this quadratic form. And locally, the 2,0 part here is generated by a symplectic form that is of the form dz1, which dz2 may be altered by a holomorphic function without zeros. So we have seen that we can pass from weight 1 to weight 2 on the level of linear algebra, but also on the level of geometry. But I mentioned that there's also a way of, so this was this thing, this way, wedge taking just wedge 2. But there's also a construction which is called the Kubercete construction, already used by Deligne and also Piatetsky, Shapiro, Shafarevich, that associates to a weight 2 Hodge structure, a weight 1 Hodge structure. This would here correspond to associating two K3 surfaces or hyperkähler manifold, a complex torus. That's a very important construction, which we have understood geometrically only very poorly. So this is certainly one of the big open questions in the theory, and would answer a lot of questions how to understand this purely linear algebra construction geometrically. Okay, I have to watch the time a little bit. Maybe I skip the next slide. I wanted to make a little break here and talk a little bit about the lattices, so leave hot structures at the side for a moment and talk about these lattices. There are curious relations between lattice theory for K3 surfaces and standard lattice, well, maybe more better known lattice theory a la Leach and Niemeyer, which somehow is a recurring theme or observations that come up again and again. There is a relation which we don't really understand that's also studied in physics. So there's a relation to conformal field theory, what's called Mathieu moonshine, and it concerns also the topological classification in higher dimensions. We don't really know which lattices H2 can occur for hyperkähler manifolds. So far we have examples only for small rank, and roughly once you fix this H2, so the rank of this lattice, you fix the topology and you fix the topology at least up to finite ambiguity. But this urgent question I mentioned before: can we classify topologically hyperkähler manifolds? But just to show our ignorance, we don't even know how to exclude the case of rank 3. So in principle, there could be that there's a hyperkähler manifold with a lattice of rank 3 as its second cohomology. I don't believe so, but I cannot exclude it. Okay, let me skip this because I really want to focus on the complex geometry. So let me say once more what we did so far. We started with a K3 surface or hyperkähler manifold, for instance, the quartic, Fermat quartic, and then we looked at the second cohomology that was a lattice, turns out to be of rather high rank, 22, which naturally comes with a complex decomposition as a complex vector space in 3 parts, 2, 0, 1, 1, and 0, 2, which not only depends on the topology, but really on the equations you've picked or on the complex structure. Now, of course, you wonder, what do you do with it? So the first thing you notice on the side of linear algebra, so Hodge theory, you can start moving this vector space to 0, together maybe with a 1, 0 space. So if you decide you just move this to 0 part a little bit, then you define the 0, 2 part as its complex conjugate, that's a condition on the Hodge structure, and define the 1, 1 part as its orthogonal complement. Okay. Now, what does it mean geometrically? And it turns out, and this is the surjectivity of the period map, which goes back for K3 surfaces to the 70s, and is more recent for hyperkähler manifolds, that roughly every Hodge structure you can put on this thing, so every decomposition like this, compatible with these two conditions, so complex conjugation between 2, 0 and 0, 2, and so on, comes actually from a K3 surface or hyperkähler manifold lambda. So if you give yourself, you start with 1 as 0, then you get the Hodge structure, then you can deform the Hodge structure, and it still comes from some other K3 surfaces or hyperkähler manifolds, which you don't know exactly what it is, but you know it's there. So there, you can go in both ways. You can either give your, for instance, the K3 surface in terms of a Fermat quartic, and you associate to it a Hodge structure of way 2, or you can go back via this surjectivity theorem by saying every Hodge structure you can put on this H2 actually comes from some K3 surface. So you find a polynomial equation. Neither of these two directions is completely trivial. So even for the Fermat quartic, it's very hard actually to describe the Hodge structure on H2. And it's even harder if you deform the Hodge structure on H2 somehow to say what happens to the equations, to find the equations that define the, that describe the geometry. There's, however, you can, however, prove certain things. For instance, you can characterize certain properties of K3 surfaces. I mentioned before that not all K3 surfaces are algebraic. The same holds for hyperkähler manifolds. Very many of them are, but not all can be described by algebraic equations. And in fact, there's a result that allows you to, just by looking at the Hodge structure, to tell you when the K3 or hyperkähler manifold can be described by equations. So this is the notion of being describable by algebraic equations, so as the zero set of polynomials. And on the right-hand side here, you see a condition that only depends on the Hodge structure. So the interplay between this lattice and this complex vector space. And the condition is whenever there exists an alpha in this intersection that has a positive square, so there is this intersection pairing on this lattice, then that's an if and only if, then the surface or the hyperkähler manifold is actually algebraic. Okay, so you see, although the transition, so the translation from one side to the other is often complicated, you can use this to describe, for instance, the locus of those K3 surfaces and those hyperkähler manifolds that are can be described by polynomial equations. Okay, now I come to the analog of the result that we know for Riemann surfaces and for Torelli theorems. That is really some of the most important single theorem in the whole theory. That's the global Torelli theorem. That's due to Piatetsky, Shapiro, Shafarevich, and Rappaport Burns in the two-dimensional case, and to Verbitsky in the high-dimensional case. So if you look at two K3 surfaces or hyperkähler manifolds, and you want to know when are they isomorphic, so when is there bijective biholomorphic map between the two, so that's the left-hand side here. And again, on the right-hand side, you find something that's only in terms of the Hodge structure. You want an isomorphism of the lattice that is compatible with the Hodge decomposition. So this is the Hodge decomposition, 2, 0, 1, 1, 0, 2 part. And you also want this to be compatible with the intersection pairing. So you want this to be orthogonal. And in higher dimensions, there's a technical condition. I won't go into this that you have to add, for which you have to know a little bit more about the topology, but never mind. Again, that's a classical result by now in the theory. But as soon as you drop certain conditions on the right-hand side, so certain parts of the linear algebras on the right-hand side, we don't really know what happens. For instance, you could again try to drop the compatibility condition with the pairing. And then we don't really know, what does it mean if you have an isomorphism of Hodge structures, of integral Hodge structures between two K3s? What does it mean for the K3s? We don't know. Or you could drop or you could alter the coefficiency instead of a lattice, so something Z module, we could look at the Q vector space. That poses an interesting question, and this leads naturally to the theory of to the Hodge conjecture for K3 surfaces. So I'll briefly talk about the Hodge conjecture for K3 surfaces. There's one aspect that that is known on general grounds. That's the Hodge conjecture for K3 surface itself. This asks the following question. So again, on the left-hand side, I look at the Hodge structure of the K3 surface, and I look at this intersection between the 1-1 part and the lattice itself. Remember, I told you this is the rank of this is an interesting invariant of the Hodge structure. It's a sublattice of the full lattice. And suppose now you pick a class in there, non-trivial class. And then the Hodge conjecture would ask, can this class or the pairing with this class be interpreted via integration over a Riemann surface that sits in S? So Riemann surface in the surface S really means a Riemann surface that you embed with a holomorphic map into your complex surface. This conjecture is actually known as a special case of the Lefschetz 1-1 conjecture. There is an analog which I alluded to before, which is the Tate conjecture. This is much harder. It's known also for K3 surfaces, but it's much harder to prove, and it's actually not known in general. But there's another aspect of the Hodge conjecture. But now you're not talking about one single K3 surface, but you talk about the product of two K3 surfaces. And instead of looking at a class in the sublattice, you look at the morphism between the two Hodge structures, and then that links it to the Torelli theorem I mentioned before. And you want this to be compatible with the Hodge structure. That means the 2-0 part is mapped to the 2-0 part, the 1-1 part is mapped to the 1-1 part, and so on. And then the Hodge conjecture asks, is there now a cycle on the product, so a surface on the product? So maybe let me draw a little picture here. You have, you really have, let me write this in this way. So this phi also gives you a class in the cohomology on the product, and you ask whether the pairing with this class is actually given by integration over surface alpha. So this theorem is open. So this conjecture is open even for this specific case. Due to a result by Buskin a couple of years ago, we know the answer if the phi itself is also compatible with the quadratic form. You see, so compatibility with the quadratic form helps you, although we have changed the integer by the complex, by the rational numbers. Okay. But we don't know what happens if you don't have this orthogonality condition. And it shows you once again that there are natural things you can do for the linear algebra side, so the Hodge theory, for which we don't have a geometric analog. We don't know how to interpret these some elementary constructions on the linear algebra side geometrically. And this is where more abstract notions come in and help you to explain a certain phenomena. And I will want to talk about two or three. Remember when I've asked these questions that come up once you look at a KT, so it's about curves and curves passing through points, and then there were bundles. So let's first look at points and curves, and both. So everything I say now is also can also be seen as kind of linearizing, and I use Chow groups and Chow motifs. So it's like taking cohomology, so it's also linearizing the geometry. Maybe this is like half linearizing the geometry by looking at the Chow group. So we're looking at points on the K3 surface X, and look at the Chow group, and just introduce finite linear combinations, abstract linear combinations, just formal things of points. That's a huge group, and you divide out by a certain equivalence relation to make it a reasonable group. And then, of course, by definition, these things you can add. So this is the analog of the elliptic curve. You know we can add points on an elliptic curve. That is much of the appeal of elliptic curves. And here you can also add, but the group is much bigger even after dividing out by this equivalence relation. And the equivalence relation really asks, and this is where curves come in, 2 points are said to be rationally equivalent if you can find a rational curve passing through x1 and x2. So then these 2 points are actually equivalent. It's not all, but there's some natural generalizations that make this group. So then you have this Chow group that remembers curves and points on the surface, and then you can see that still Hodge theory has to tell something about this condition, and that's this result. Suppose you have a biholomorphic map from S to itself, and then you can look at its action on the cohomology, and you can look at its action on the Chow group. Of course, any automorphism acts on the Chow group by just mapping points to points. And there's a result that says you can determine the action on the Chow 0 of the surface if and only if you know it on the 2-0 part. And that's a special case of the Bloch-Petersen philosophy that in general is completely open. Even here, there are questions that are open. For instance, we don't know what happens if the order of this is infinite. So here the assumption I didn't put this. The assumption is that this is an automorphism of finite order. You can also use Chow groups to linearize not points on the K3 surface, but actually the K3 surface itself. So linearizing S, and that follows Grothendieck's general philosophy of motifs. So we replace geometry by a linear category now. That's the category of motifs here. So replace any surface by an object in some linear category. So what does it mean to have a linear category? So if you look at geometric objects, then maps between them are just like biholomorphic maps or algebraic maps from S1 to S2. That's of course just a set, has no further structure. On the left-hand side, however, the morphism space between two objects in this category is really a Q-vector space. This is what we call the Chow 2 group of S1, S2, which then measures maps from surfaces to products S1, S2, and divides out by a linear equivalence relation similar to the one we've seen before. So that's good. Somebody replaced wild category by a linear category, which very much behaves like the category of vector spaces. And there's one big open question, for which we have gathered evidence by looking at K3 surfaces, but the conjectures in general, is this thing here always of finite dimension? And this has to be explained in the correct way. And for K3 surfaces, this means that if I take the wedge 22 of HS, I want this to be 0. So that's an open, big open question, and the Kubercete construction would help us to answer the question. Okay. Now, to show you that these abstract notions actually help you to explain certain phenomena you see on the level of on the side of the Hodge theory, I put down this theorem. You can either view this as a motivic Hodge conjecture or as a motivic Torelli theorem, and it says if on the left-hand side I give myself an isomorphism of Hodge structures. So, but now with rational coefficients here. I keep the compatibility with the intersection form, and I keep the compatibility with the Hodge decomposition. So a 2-0 part on the left-hand side goes to the 2-0 part on the right-hand side. But I relax the coefficients. So instead of Z, I put Q. If I put Z, then the two surfaces are isomorphic. If I put Q, geometrically we have no explanation to it, and it turns out there is a abstract geometric notion on the left-hand side that says that this condition is actually equivalent to the two motives, so these two elements in this linear category to be isomorphic. Okay. Again, we don't really know, or at least we have an idea, but we can prove it. What happens if I drop not only relax the integers to Q, but drop this condition? That's open, but at least in this case, we don't know. We know what to expect. Okay. Yes. Maybe, so I want to talk about bundles as well. So there's also a way of linearizing bundles that leads to triangulated categories. But maybe let me just skip this. There is a categorical Hodge Torelli theorem that also explains, again, the isomorphism of Hodge structures with rational coefficients. But let me maybe skip this and instead go to the last slide, where I wanted to explain that you should not think of K3 surfaces and hyperkähler manifolds as living in some special corner of algebraic geometry. They are special geometries with a rich structure, but they come up frequently in places of algebraic geometry where they shouldn't play any role. And I picked here on the last slide probably the most prominent example, that of cubic hypersurfaces, where miraculously K3 surfaces and hyperkähler manifolds play a role. So cubic hypersurfaces are surfaces, are complex manifolds that are described by a cubic polynomial. So for instance, you could again look up, you can again look at the Fermat equation. Now on 5 variables, that's a Fermat equation, and you look at the 0 set of this in the complex number, conveniently compactified at infinity, and then you get what is called a cubic hypersurface. So these things are really of a completely different geometry. They rather behave like projective spaces. So they have positive curvature and not at all like K3 surfaces and hyperkähler manifolds. But it turns out that geometrically and Hodge theoretically, hyperkähler manifolds come in, on K3 surfaces in particular, in this area of algebraic geometry, and this has been intensively studied for 10 or 15 years now. Geometrically, you could look, for instance, at the Fano variety of lines. So these cubic hypersurfaces, they live by definition in some linear space, and you could look at the set of all lines contained in this cubic hypersurface, and they form a variety, and turns out this hyperkähler manifold of dimension 4. And more interestingly, maybe, is that purely looking at the linear structure, the Hodge theory of the cubic, it turns out, and this has been studied by Hassett originally, that very frequently there exists a K3 surface as X, such that the Hodge decomposition you have for the cubic fourfold is the same, or roughly the same as the Hodge decomposition for the K3 surface. Part of this picture is understood geometrically. So by construction, the role of the Farnow variety of lines is understood. The geometric meaning of the K3 surface is not understood at all, and it's probably doubtful that it has a proper geometric meaning. And this is another instance where these abstract ways of doing geometry, using motives and categories, actually gives you the proper explanation for what we observe on the linear algebra side of Hodge theory. It turns out that in these cases, the derived category is contained in the derived category of the cubic hypersurface, or there is a part of a relation isomorphism of the essential part of the motive associated to the K3 surface and the motive of the Fermat cubic, for instance, which cannot be explained geometrically, classically, but you need these abstract notions. And I think it's 10 o'clock and I should stop here. Thank you very much for listening.
Thank you very much for this fascinating talk. So I have seen one question already in the chat, which is by Bernd Ammann, and I read it. Are there non-trivial moduli spaces of hyperkähler manifolds in complex dimension bigger than 2? So Klaus Sulek already answered in the affirmative, but maybe you want to say some words to it.
Okay, I'll just confirm, Klaus is correct. Yeah, so these hyperkähler manifolds, they come in dimensions. I wrote down some examples here of Betti numbers. You see they are governed by these Betti numbers. So for instance, this would be the case of K3 surfaces. The moduli space is 19-dimensional for the algebraic ones and 20-dimensional for the complex ones. This one would have a 5-dimensional moduli space. And this one, that's why I pointed this one out. This one would have a 1-dimensional moduli space. If you allow all complex hyperkähler manifolds, if you only look at the complex, the algebraic ones, it would be an isolated point. And somehow we don't believe that hyperkähler manifolds appear, even algebraically, appear isolated as isolated points. But in this case, we don't know how to exclude this. But my guess would be they always come, even the algebraic ones come in families. And the complex certainly always has 1 dimension. And I haven't talked about the metric aspects. There's always the Tisler space construction for the hyperkähler metric. So every hyperkähler manifold at least occurs in a 1-dimensional family of complex manifolds. I hope this answers them.
Okay, so then somebody raised his hand, Boris Kuklikov. So I just allow him to speak. Maybe he can ask the question. Boris, do you want to ask a question or? Okay. Can you hear us? Or maybe you want to ask a question via the chat?
No, he wrote he doesn't want to ask anymore.
Okay. Okay, then are there other questions or remarks? Yeah, sorry?
There is one more.
Okay. So this was by Fabrizio. Okay, so do you want to ask?
Yeah, well, I think it's. I wanted to ask a question in the last part on the cubic hypersurface. Then the occurrence of the K3 surface is through this embedding of the derived category of the K3 surface in the derived category of the cubic hypersurface.
Yes.
Why? Yeah. How does it go? How is this unique? How does it happen?
Okay. So there's not always a K3 surface, but so it happens frequently that you can observe a K3 surface just on the level of Hodge theory, and you don't know what it means. And the answer really is, in this case, whenever there's a K3 surface, with a hot structure essentially being the hot structure of the cubic fourfold, then the derived category embeds into this derived category of the cubic. But the K3 surface itself is not unique. So that's why I believe there's no geometric interpretation for the K3 surface, but only this categorical interpretation using these derived categories. And this was first proved generically by Eddington and Thomas. It essentially shows that the picture of Hassett and Kuznetsov coincide. And then recently in this big paper by Bayer and 5 co-authors, they have completed this to prove this for all cubic hypersurfaces that come associated with the K3 surface.
So if I may ask again, so this happens for this countable, union of subvarieties?
Yes.
Okay.
Well, one question at that point. I mean, at some point, people believed that this was related to the rationality of these cubic fourfolds. Is there any more progress on that?
No. So this is these 3 points here down here. This is where I wanted to finish by talking about the Lyrod problem. So there is the general conjecture. There were two. Actually, there are 3 conjectures. One by Kuznetsov, one by Hassett, and one by Galkin-Schinde. Detecting which of the cubic fourfolds are rational. So for the non-experts, rational means there's a big open subset that just looks like C4. And the conjecture of Hassett said this is the case if and only if there is a K3 surface with the same hot structure. Kuznetsov's conjecture was this is the case if and only if there's a K3 surface sitting in the derived category. These 2 conjectures are now shown to be completely equivalent. And then there's a conjecture that's not compatible with these 2 by Galkin and Schinde that have to do with describing the Farner variety, relating the Farner variety with this K3 surface. And that would predict rationality for a smaller class of cubic fourfolds. But it's totally open.
Okay. Any other questions? Orally or via the chat? Seems not to be the case. So then let's thank Daniel again for this very nice talk.
Thank you very much for listening.